Good afternoon, everyone. This is Srikumar Maganti from EDS Technologies. Today, we are going to focus on the webinar, Modeling and Simulation of Battery Cell Module and Pack Engineering. Before getting into this particular webinar, I would like to give brief introduction on EDS Technologies. EDS Technologies Private Limited has started in 1995, providing technology solutions across India, and we have been platinum partners with Dassault Systems for more than 2.5 decades. So we have our headquarters in Bangalore, and we have branch offices in multiple locations like Pune, Mumbai, Chennai, Coimbatore, Hyderabad, Kolkata, and Noida. So we provide complete range of solutions for CAD/CAM, CE, PLM, and also the data intelligence solutions across India. And we provide a complete range of solutions for design, simulations, manufacturing, as well as the product lifecycle management. So we provide the brands of Dassault Systems like CATIA for product design excellence, Enovia for social collaboration platform and product lifecycle management, and also Delmia for digital manufacturing, covering end-to-end manufacturing solutions, say like from process planning to assembly simulations, factory flow simulations, machining, and also production planning and scheduling, etc. And also we are providing solutions for mining segment as well in the brand of Geovia coming from Dassault Systems. And we also cater to 3D printing technologies. We are one of those early pioneers introducing 3D printing technologies in Indian market. And today we are providing our solutions through EOS, which is Electro-Optical Systems Germany. We provide metallic and polymer printers, which are industry functional printers, basically meant for batch production. Then we also provide solutions for virtual twin, geospatial analytics, like with the GIS solutions, geographical information intelligence solutions, and also we provide solutions meant for virtual twins, and we have been providing even military and defense solutions using visual simulation solutions in Indian market. So we have more than 2,000 customers across India who believe we are the trusted partners for them, and who are our active partners. And we have given our software solutions to more than 5,000 customers across India, again covering automotive, aerospace, defense, industrial equipment, mining, high-tech electronics, consumer goods, energy processing utilities, and many more segments. So this is our a brief introduction on EDS technologies. And today's webinar will be focusing on modeling and simulation of battery cell, module, and pack engineering. So as you all know, like battery engineering has come a long way, making its presence highly felt, especially in the EV segment. Again, it caters to all the EV segments in terms of two-wheelers, three-wheelers, and four-wheelers, and also heavy vehicles, electric buses, etc. So it becomes a core of electric vehicle product development, basically. And today, if you see the customers, they are expecting their vehicles to be affordable at the affordable cost. Again, covering the long range, capable of fast charging, and also looking at the safety and the reliability of the battery packs that they have. And also they are looking at the optimizing the thermal management of battery and the whole vehicle, and able to predict performance and aging of battery, and also looking at how it can integrate with other systems like electric powertrain or HVAC or power electronics. And it's basically the multidisciplinary dimension that they are looking into. So today's webinar will be focusing on battery engineering at cell level, and also battery at module or pack level, and also battery at vehicle integrations level as well. So we will be looking into some of those important factors of battery engineering, which will cut across the thermoelectrical analysis, for thermoelectrical losses calculations, and also strength, stiffness, and durability, and also looking at the safety parameters, especially with respect to abusive elements like crash, drop, or impact, and also the reduced order modeling. So today we have our expert speakers who will be talking about the complete solutions from Dassault Systems on battery engineering, covering design, simulations, testing, and validation, and also the certification from the bodies like ARA and INCAT. So I invite our speakers, Mr. Siddharth Prabhakar and Prakash Pagadala. So they are well versed into battery engineering, like especially catering to EV segment. So Mr. Siddharth Prabhakar is working as industry process consultant at Dassault Systems India for almost 4 years, and he has been actively working with most of those EV OEMs across India, and also the startups and battery manufacturers and their suppliers. And he's also well versed in model-based systems engineering and 1D simulations, and also the electrical wiring harness, which is a critical component of EV product development. And then he has been supporting tens of EV startups across India, in terms of making use of these solutions and also incorporate best practices throughout the value chain. And he provides the best solutions, which are basically multidisciplinary systems engineering solutions to help customers save valuable time and solve their problems on time. So I welcome Mr. Siddharth Prabhakar onto this panel today. And also we have another expert speaker, Mr. Prakash Pagadala, who is well versed into simulation solutions. He is the industry process consultant with customer process experience team at Dassault Systems India. And he has been providing his expertise on the simulation solutions for process automation and customization, fatigue simulations, advanced dynamic analysis, and also more into the transportation mobility sector for automotive engines and powertrain durability. And he has been working with various industries, providing the critical complex simulations solutions. And he has BTech in mechanical engineering from Kakatiya University, and also the master's in mechanical design. So I invite Mr. Siddharth Prabhakar to take over from here, and he'll be talking about the battery engineering from the perspective of design and also the systems engineering. Over to you, Mr.
Thank you, Sri Kumar, for the warm welcome. Hello, everyone. Good afternoon. Let me share my screen. Thank you all for joining this particular webinar. So I'll be taking you through the introduction of the battery system modeling as mentioned by Sri Kumar. And apart from that, in today's session, we'll be also talking about the battery cell engineering and battery pack and module engineering aspects as well, which my colleague Prakash will be talking more about. So just before we enter into the topic, a bit of introduction about Dassault Systems for the ones who might not be familiar about us. So we are a purpose-driven company. We combine science, art, and technology. Science, art, and technology for a more sustainable world. We have close to 20,500 people working across 135 countries from about 180 offices worldwide. Within India, we have about 8 offices and about 2 R&D labs in India, one in Pune and one in Bangalore. We have an overall revenue of about 4.8 billion euros and an operating margin of about 34.3%. Globally, we have close to about 15,000 partners and across about, I would say, 300,000 customers across 11 industries, and with a game-changing solution called the 3D Experience Platform is what they're using. So a bit more about our legacy itself, and we have a very well-proven track record in this particular industry. We started off back in 1981, wherein majority of our customers who started using our CATIA solution was in that particular decade itself. And eventually we started expanding our solution, and the first entire digital mock-up of an aeroplane, which was done in collaboration with Boeing, was done on the CATIA tool itself. That was back in 1989. Eventually, we also integrated product lifecycle management within our solutions, and this was in the decade of 1999, and this was done in collaboration with Toyota. And eventually we came up with our revolutionary tool, which is called the 3D Experience Platform. And this was back in about 2012 is where we did this. So rather than our customers just designing and modeling their products on the platform, on the 3D Experience Platform, they can actually generate various experiences or 3D experiences as we call them. Now, eventually, we have moved towards more of virtual twin experiences for human beings, wherein we have been capable enough of building entire human models of virtually modeling and simulating these models as well, how we typically do it for the different engineering components. Yeah, so let's jump into the topic of the digital solutions which we have for the battery industry. So we at Dassault Systems have an extensive solution suite for the battery industry, starting from the molecular level and up till the system level. Now within them, we have dedicated workflows which are available for these individual graphics which you're able to see in front of you. We start with something called as is the battery materials design, then we move to battery cell engineering, battery module and pack engineering, battery systems module, battery management system design, and device integration. Now, within these multiple, I would say, different bundles which you can see here, there are interconnections which are available. And all of this is coming from different solutions of ours. So a few of these capabilities are coming from one of our brands, which is called as BioVia, which typically takes care of the molecular level modeling, which is at the molecular scale. How do you work on these different cell chemistries and those sort of aspects? Now, using the capabilities of the CATIA and the Simulia solutions, you're able to build your battery cell design and your different simulations which you would be doing, which Prakash would be talking more about. While on the upper half of this particular graphic, we talk about the behavior models of different cells that we can perform. These could be various mathematical models that you can actually simulate at a cell level, module and pack, and system integration level as well. And further, you can come back to the bottom again once and integrating all of these different aspects and obtaining your final simulation results. So this is a basic snapshot of the end-to-end workflow which we have. But within these individual solutions, we have dedicated workflows which are available. So the image on the left-hand side above, you can see is the molecular modeling aspect, wherein we do an end-to-end battery material testing and simulation studies for the molecular and test different cell chemistries. Then further, we have different workflows which are available within the battery's cell engineering level itself. It starts by designing your cell, doing different thermoelectric losses analysis, the lower order modeling, your safety analysis, and multiple other aspects as well. Further, we also move on to the module and pack engineering. Now, within module and pack engineering, we start by designing our battery packs, the entire battery pack. We also do a testing, the strength, stiffness, durability testing, building different cooling circuits to provide cooling to this particular battery pack, doing various thermoelectric losses, and the safety analysis is something which we can do at this particular layer. The layer which I'll be going a bit more deep into is the system modeling engineering layer. That is the concept stage of it, wherein we start by defining something called as the electrochemical model. We start by defining our cell models, defining different aging parameters, our different cell models itself, and further we move into the battery pack simulation. And once we're done with battery pack, we try to integrate this particular battery pack with our vehicle level, and then we try to further integrate with the different digital twins that can be built. But talking about where and why or how this particular different solutions can be brought into one place, and that place is basically the 3D Experience platform. Now, within the 3D Experience platform, a user can do product engineering, test management, product management, and program management. Now, at the product engineering layer, one can actually do a modeling and simulation and design exploration of their different cells, packs, and batteries basically. Now, these cells are not limited to basically any given sort of cell or form geometry. It can be a cylindrical cell, it can be a prismatic cell, it could be a pouch cell. You can do various design and exploration. Wherever you have designed your cell, the entire jelly roll model, it can be simulated in the same environment as well, which again, Prakash would be going into a bit more detail. Further, the 3D Experience platform is also capable of handling various test managements as well. So from process and automation to change management and collaboration and analytics is something that you can do within the 3D Experience platform. So you can set up various DOE studies or design of experiments to do various explorations of your different battery cell, to run various simulation studies is something that you can use the platform for. Moving on to the next step is the validation and the certification layer. Now, since everything is done within the 3D Experience platform, you actually have a capability of maintaining your entire requirements. Your vehicle level or your component or system level architecture can be something which you can do with the 3D Experience platform. And you can also maintain an end-to-end traceability of the different requirements that you have written within the platform. Further, like I had mentioned, the PLM is integrated as a part of our solution. So you have the project management and program, the entire governance already taken care of. So you can have different workflows or the APQP process, which can be established within the platform, and you can further collaborate and work better as a team internally in your organization. So let's not wait a bit more, but let's jump into the topic of battery system simulation, which we can go a bit more deep into. Now, before we go into the topic itself, let's try to understand the various design consideration or the various outcomes which you can generate by just doing the cell or battery pack or vehicle level simulation at the system level. This would start basically, you can do energy density analysis, wherein you want to improve the energy density in your cells and overall the battery pack as well. Further, you want to test different cell chemistries and different technologies that you're working with. You want to compare different chemistries and see which particular is the best outcome for you. You further want to do different safety analysis. You want to avoid scenarios such as thermal runaway, do an end-to-end thermal simulation of your cell and battery pack. That is something which you can do. Further, different charging time. So charging and discharging your cell for various high C rates and discharging it is something that you can easily do with the 1D models. Aging simulations is something which typically manufacturers are looking for. They are looking to do various aging simulations on the calendric and cyclic aging of their cells. The next is how the temperature spread across your entire battery pack is. So you might have a battery pack which is split into a number of modules, or you have a single module, but with a number of cells in series in parallel. How do you find how the temperature spread is in this particular entire battery pack? Further, the sustainability and recycling is something which we also have the capabilities of. Yeah. So coming on to the workflow, you can see it is a 7-step process where we start from the left side, which is the first level is the electrochemical behavior, wherein we start by defining the electrochemical behavior of our cells. Now, within the platform, you have a capability of building either P2D models or ECM models. P2D models are basically the electrochemical models, while ECM models are the equivalent circuit models. Now, depending if you're an EV manufacturer or if you're a cell or a battery pack manufacturer, you will be having a given amount of data which you can access, which is the cell chemistry layer itself. So depending upon the workflows that you are following, you can either start from the electrochemical behavior model, or you can start from the equivalent circuit model, which I'll be talking about a bit more in the next slides. Further, once you're done with that aspect, you go into the next level, which is the electrothermal behavior aspect of it. You start by defining your thermal models, discretizing it into multiple layers, and we are still at the cell level. So we have not gone into the pack level, but at the cell level itself, defining the various thermal properties of your cell is something that the user can do. Yeah. The next level is where we try to define different aging and degradation models. So the tool which we'll be using in this case is called as Dymola. Dymola is basically a 1D modeling tool wherein different degradation and aging models are already present. The user just needs to enter the parameters and run the simulations for different cells here. Once we are done with the cell level simulation, that's where we move on to the next level, which is the module and the pack level. Within the module and the pack level is where we start defining and integrating different cooling circuits for our cells, defining it into number of modules, defining how many cells are in series, how many are in parallel. Those sort of aspects are taken care at the module and pack level, which we'll be further seeing as well. The next part is what we do is at the system level, wherein if you're an EV manufacturer, you have a battery pack, you have a vehicle, you want to understand what kind of range estimations that you can obtain, what kind of temperatures your battery pack is going, how does your battery perform if you're charging it at a high C rate, and how does the discharge of the battery pack look? How do I also integrate various auxiliary systems in my at my vehicle level is something which you can do at a system level simulation. The next step is where you can actually build digital twins. Now, digital twin is a concept where you are taking a given amount of data from, for example, the entire battery simulation that you've done here and the further simulations which you'll be doing in using the Simulia tool, and integrating it all at one place and trying to get an end-to-end simulation and an end-to-end model built for your particular product or system. So let's start with the first layer of ours, which is the electrochemical cell behavior model. Now, the graphics which you're able to see here are basically the different models which are available within the solution for you. And with the platform, what you'll be doing is, or with the solution, it's a pick and drop approach. So all of these models are already present for you. All you need to do is just pick and drop them and fill in the different parameter values. All the empirical relations and the empirical formulas are already integrated within the blocks which you can see here. For example, if you see the electrochemical block, so the electrochemical block is already has all the different uh, empirical formulas already present inside, and you just need to fill in the parameters. What you can obtain at this layer is the different concentration of lithium ions. You can understand what is your potential of your electrolyte, your active solid electrode matter. You can benchmark different materials and cell technologies. So using the material modeling solution, so we have a solution within our portfolio which is called the BioVia tool. Using the BioVia tool, you can build different cell chemistry and materials and do the validation for them within the Daimola tool itself. Further, what you can also do is perform analysis at the cell level and reuse these models at the system and pack level as well. Now, like I mentioned, there is a workflow available, or there is an interconnection which is available within these solutions. So what you can see here are different empirical formulas which are already present inside these models, but the ones which are marked in green color are the values which are coming from the material modeling solution of ours. So these are basically different transfer coefficients and different diffusion coefficient values which you have obtained from the molecular level modeling, which you're further using to do your cell level simulations, which will help you to get outputs such as your concentration of your lithium ions, your electrolyte concentration, and other such aspects as well. Yeah. But like I'd mentioned, you have an option either to start with the electrochemical model, that is the electrochemical models itself, or the P2D models, or you can start with the equivalent circuit modeling. If you start at the equivalent circuit modeling layer, these models are basically divided into three submodels. And these three submodels are nothing but your electric model, your aging model, and your thermal models. Within these blocks, the user needs to enter these parameters of different values. And I'll be talking a bit more upon that, what those values are. But using them is what your end-to-end cell simulation, and further these models are used to do battery pack and vehicle level simulations as well. Yeah. So let's start with the first layer, which is the electrical cell behavior. So Daimola basically supports both at cell level itself. It supports table-based modeling and equation-based modeling, but we'll talk about table-based modeling here, wherein what we're trying to do here is we have further narrowed down our battery cell into a basically a circuit of different resistors and capacitors which are connected in series, and within them we are defining the various values using lookup tables. Now lookup tables can be in different data formats. It can be an SDF file, it can be a .mat file, or it can be a TXT file. Using these lookup tables, now these lookup tables can either be a 2D lookup table or a 3D lookup table, which will typically have parameters of state of charge, temperature, and current values. If you do not have these tables available with you, we do have a workaround available in using which you can create these different table datas which can act as inputs for your electric model. This is a quick snapshot of how these table-based models are run. So on the left, on the top, you can see you have a circuit basically of your cell, which is basically a series and parallel of different resistors and capacitors. Using them and putting a different charge and discharge value, we are getting a few outputs of our serial resistor, our resistors in parallel, and the capacitor. Using these values, we create an SDF file which looks something of this sort. And this SDF file is basically acts as an input for your electric model of your cell. And this is one way is how we try to capture the different cell chemistries as well. Because for individual cell chemistries, you will have different SDF files. And these SDF files would represent how the cell simulation or how the cell performance is at a particular discharge and charge level. Yeah. So once you're done with the equivalent circuit, or the electric model of the cell, we start by defining our thermal models. Now you have ready-made blocks available both for cylindrical and for prismatic cells. Now within cylindrical and prismatic cells, the user has the capability of actually vertically and horizontally discretizing it into multiple layers. The benefit of doing that is when you are doing a cell level simulation, the user can actually obtain values of the temperature of the cell throughout the particular cell itself. So for example, if you can see this particular image here, you can actually notice that there are multiple small red color blocks which are available. These blocks are nothing but signifying that the cell has been divided into multiple layers, and the parameters or the results for individual layers can be obtained while doing the simulation. And this is a capability which exists with Daimola, and the same can be obtained at a battery pack level as well. Yeah. So coming to the next block, which is the aging cell model. Now, within aging cell model, we support both calendric and cyclic aging. Now, cyclic aging is a process where, depending upon the number of charge and discharge cycles that you're doing for your cell, your battery will eventually degrade, and this degradation can be accounted for using the cyclic aging simulation, while calendric aging simulation is nothing but over a period of time, due to the cell chemistry behavior itself, your cell will lose a certain amount of charge and capacity loss. So this can be accounted using the calendric aging. And these models are again embedded with various empirical formulas already. And these empirical formulas are what are used to define your capacity loss and your inner resistance as well. So based on these calculations, the feedback is sent to your ECM models or your equivalent circuit modeling, and the final results are obtained for the different degradation and aging scenarios. Yeah. So the next step, once you're done with the battery cell simulation and battery cell modeling, you enter into the next step, which is the battery pack level itself. Now, within the battery pack, we support two simulations. One is called as the scaled simulation, and another is called as a discretized simulation. The outcomes and overall, the use cases to use these sort of battery packs is different for each scenario. The scale simulation is typically done wherein you are doing more long-term studies. For example, you're trying to understand the aging simulation, or you're trying to understand over a long term how does your battery perform. That's where you use scale simulation. So these are basically easy to implement, and quicker simulation times can be obtained here. While the ones on the right side are discretized battery pack, these take time, and these are typically done wherein you're trying to do more detailed studies for different cell comparison or different material studies is what you're trying to do. How these are different from each other in another layer is also that the scaled simulation, what the tool does is it assumes one cell, and this cell is assumed to be the same throughout the battery pack. But that's not the realistic scenario again, because depending upon the connections that you have made, be it in series or be it in parallel, the properties would be different. That's why the scale simulation is typically used for longer studies, while the discretized simulation is done at a cell level and individually itself. Now, let's go a bit more deep into the discretized simulation layer itself. So within discretized simulation, the user has the capability or user has the option to define the cell configuration, the thermal separation, and the housing parameters. Within cell configuration, you can define how the cells are connected in series and parallel, how many number of cells are there overall in your battery pack, how many modules are they further divided into. Within thermal separation, you can define the heat transfer properties between the different cells, either is it ideal, static, or dynamic heat transfer. Further, you can also define the housing heat transfer parameters as well through different heat ports which are already present. And these can be either material based or directly, but the user has the capability of defining these properties of heat transfer for the housing block as well. Yeah. So as a next step, once you have determined your thermal values, you've determined your entire battery pack, what sort of a structure you have, the tool also helps you with the capability of defining a cooling circuit around your battery pack. Now, this cooling circuit could be a simple cooling circuit with just an adapter and a simple coolant flowing through your particular battery pack, or it can be a detailed cooling circuit with different heat exchanger control switches, control valves, your different coolant studies at a particular temperature. You can define your coolants, and those sort of things can be done using various libraries which are already present within the tool, and these can be used to define the different cooling circuits. The testing of the cooling circuits or the 3D aspect is something which you'll be doing with the different solution, which Prakash will be talking about. But at the 1D layer, trying to understand what sort of heat outputs can my models generate is something which you can do using Daimola itself. Yeah. Further, what you can also do is a system integration and analysis. Now, within this layer, what you're trying to do is you're also trying to account for different auxiliary systems which are a part of your vehicle. So if you can see the image on the right side, it's nothing but the test bench which we typically use to simulate an EV. Now, within this EV, we have our energy supply, which is our battery pack basically. We have our driveline, which is our motor. We have the chassis, which is our vehicle block itself. And we also have a thermal management system. In this case, it's the HVAC unit of the vehicle. Since the HVAC unit will be also consuming power from the battery, we'll also try to see what sort of a range can be obtained if these sort of scenarios are on. So you can define a vehicle cabin model for a particular temperature that you're maintaining at your cabin. So you can see at the top here how your battery performance is changing while your thermal management system is trying to maintain the cabin temperature at a particular level. Further, you can also define various drive cycles. It can be either an NEDC drive cycle, WLTP drive cycle, or it can be a custom drive cycle to see how your vehicle is performing. So those sort of scenarios can also be done using the platform. And the last step, like I mentioned, is the digital twin simulation. Now, once you have all of these parameters or different outputs which are being generated using the Daimola tool itself, further it can be integrated with the different solutions within our portfolio, and to do a digital twin of your entire vehicle or your system level simulations can be done. Yeah, so this slide basically talks about the design of an electric vehicle and how different interactions of different systems work within the vehicle. So you have your battery cell design, wherein you have defined your different cell chemistries, your aging behavior, electric behavior, thermal behavior. You have benchmarked your cells at a particular performance levels. You have done your analysis at that level. Further, you're building your battery packs. It can be a scaled simulation or a discretized simulation, depending upon the study that you're trying to do, and you can also define your battery cooling circuits around it. Once you have defined that, this can be done using the cooling system design library. You can also include different air conditioning designs, so to account for different auxiliary systems. You can define your e-drive design, which is your electrified powertrains. You can define what sort of an inverter do I have, what sort of a motor do I have, what sort of a controller do I have. Those sort of aspects can also be taken care of, and the vehicle architecture of your given product as well. At the end of it, once you have done all of these aspects, the typical benefits that you'll be obtaining is to analyze the multi-physics behavior and the interactions at the chemical, electric, thermal, and the aging level. You can also develop and integrate battery systems for various applications. It can be an EV, it can be a stationary system, it can be a simple isolated battery pack as well. Further, you can design, analyze, and optimize your batteries and electric storage systems. You can calculate, benchmark, and optimize electric performance, thermal behavior, and the aging behavior of your cell. There is a seamless integration which is available within these models using the FMI capability or functional mockup interface, which is built into the tools itself. The models within Daimola can be further expanded into multiple domains. Like I had showed, you can add a thermal pack, you can add a cooling circuit, you can add different vehicle integration levels. So it's not limited to a particular domain, you can expand the scope of it as well. So with that, this is what you typically try to do. I try to run through it a bit more, but we can further go into detail based on the questions. And that is where, once you're done with the conceptual level, that's where you start with the next level, which is the battery cell engineering, which is where you start actually defining it in 3D and start making these different cell models and pack models as well. So with that, I'll hand over to Prakash, and Prakash can take you over through that aspect. Thank you.
Thank you very much, Siddharth. So once you have a broader idea of battery design, cell or modular pack designs, yeah, once you have your concept of battery cell design or the modular pack designs, then we get into a detailed study to understand a deeper insights of the design, the material, um, and how we can optimize uh, uh, the cells, modules, as well as the pack. So here we have divided the workflows, not just limited to this, but we can do a lot more. But just to give you a quick overview, we divided this entire presentation into two parts: battery cell engineering for those who are interested in understanding design and simulation of battery cells, and also those who want to procure modules and pack, we have separate industry process experience called battery module and pack engineering. One of the challenges when you start designing the cell is the design itself, because it has a lot of layers of cathode, anode, separators, and collectors, and different form factors, of course. And once you take it from design to finite element simulations and any modifications, of course the pre-processing and any modifications will eat up a lot of time. So with the philosophy of modeling plus simulation, combining modeling as well as simulation at Dassault Systems on 3D experience platform, we could able to collaborate both the design as well as the simulation. So at any point, if you want to make any changes in your design, or whatever the design changes will then go to propagate to the upstream simulations, which helps you to save a lot of time, as you can see here. So any changes, whatever I make in my finite element or the design will reflect in my design. Here is another slide on how quickly we can create a complete 3D model of a 3D cell, a cylindrical cell, and how easily we can change the shape of the mandrel, for example. So at any point, if I want to change the shape of the mandrel from circle to some other shape, I can quickly do that. And also whatever the mesh, the finite element discretization will be carried to the new model as well. So here, if you see, I'm now changing to a different shape, the mandrel from circle to a different shape. So with this philosophy of modeling plus simulation, it's quite easy and quite robust to create different form factors of cell, not just cylindrical, but also pouch, prismatic, or any other sort of a form of battery cells can be designed. Once we have the cells, of course, most of you know how the cell, at micro level, how it behaves. So during a charging, let's say from the particle, the lithium will split into lithium ion and electrons, which is a micro scale diffusion. Then the lithium ion then interacts with the solid liquid interface, which is the intercalation in in battery terminology. Then the lithium ion moves from cathode to anode through a separator, electrically insulated separator, of course not in a straight line, but the electron takes a different path as it can't pass through the separator because of the electrical insulation, which is a micro scale diffusion and sits in the anode in macro scale diffusion. So this is a continuous process during a charging and discharging cycle. And during this process, so due to the charging and discharging, during the lithium from cathode will move to anode. Along with the diffusion, there will be thermomechanical effects like the heat because of the electrical resistance, or because of the entropy change, as well as there will be mechanical changes like swelling at cathode, anode, on cathode as well as on anode. Now with the 3D Newman model, we have a mathematical framework to capture these different kinds of physics at different scales with 3D Newman model. So we look at some of the responses when we construct a cell, considering different physics at different scales. So one can estimate the temperatures, the lithium ion concentrations, and the potential at different locations of the cell. Then we can also look at the thickness deformations, stresses induced due to the swelling. Then there is something called swelling induced electrolyte flow, which is basically swelling causes electrolyte to flow in different directions in different regions and causes some sort of a dead zone. Uh, uh, Such scenarios can be studied, and also we can explore different chemistries. Let's say I want to start with an MC, and maybe I want to use LFP. How different it is, how are the temperature distributions, how is the swelling for these two chemistries. These can be studied with the 3D Newman model, and then we can also homogenize through something called model order reduction. We can then reduce the complete detailed model into a homogenized model, which can be further taken to a module and pack level for upstream simulations of the modules as well as packs. So when we start with the electrochemical simulations, we start with this can be your starting point to start with a pseudo 2D model. So here the idea is not to focus on the form factor or of the cell, but just to understand or look at the thicknesses of active material, the material properties, and area of the cell model. Here, for example, here for a charging scenario here, we can see how the lithium ion concentration has been changing at the concentration has been changing at different locations in this model for a four-step loading, where we charge, then we hold the charge, then we have a free hold, then we discharge the battery. Then we validate the material behavior based on the results and optimize if further required, without actually getting into the actual 3D model, which can be very expensive. Then we move to a complete 3D model. We create whatever we have created in the design, we take as it is for simulation with using the same 3D Newman model for different charging and discharging cycles to understand the temperature distribution, the electric potential, ion concentration, and or the volumetric staining, which is basically your swelling and other things. Of course, you can also study the effect of tab locations. For example, if tabless designs, tabs, and the placement of the tabs, etc., using a P4D model. Then you can also understand what happens to the cell, what are the thermoelectrical losses, how the cell behave for a given current rate, a complete cell, how the temperature distribution is, etc., or from through thermoelectrical loss simulation in the on the platform. Of course, we can then move to more integral or cell integrity simulations to understand the strength, stiffness, and durability. As there are certain regulations in different countries on how the cell is going to behave when there is a when it is bent, or when there is an impact on the cell. All these can be studied using the complete 3D model of the cell design. Then if there is any abusive thermal events like a short circuit, such scenarios can be studied. It can be an internal short circuit using the using coupled thermal, electrical, as well as mechanical analysis. To compute detailed electrical current densities, how the current densities is evolving in the affected area. These can be predicted and studied using the internal short circuit workflows here. Then of course the thermal runaway, we can also study how the temperature is behaving and how it is propagating through the cell. Such studies can be done. Extending the Newman model to predict the degradation in a cell when it goes through different loading cycles, which results in capacity loss or increase in internal resistance. Of course, there are various mechanisms by which uh, the actual degradation can happen, and here we consider four secondary chemical reactions that degrade the capacity, like the ACI growth, the lithium plating, or ACI reformation at the for the anode, or the dissolution for the cathode. So using using the extended or using the 3D Newman model, we can also study the cell degradation when it is for different load cycles, or even when it is not used for a longer time. Now, as you, when we are designing the complete 3D cell, it consists of a lot of elements and nodes, and that can be very expensive when you're taking the cell as it is for a module or for a pack for a it can be a drop test or a thermal simulation, or even some sort of vibration analysis. In order to reduce the computation time, it is possible to reduce the model from a detailed cell design to a homogenized cell design here, without actually compromising any details, physical as well as the entity details, the internal details of the cell. Here you can see a jelly roll model, which with a detailed layer, with all the details of the layers, has around 1.3 million number of nodes, whereas the homogenized jelly roll can be reduced to only 5K nodes without actually compromising the performance of the cell. So the accuracy will not be compromised, but uh, uh, it can be reduced for further simulations in the module as well as in packs. Then we move to the module and pack engineering, where we understand what happens when the cells get into a pack or a module and then into pack, or maybe a series of modules. So from the system specifications, we then we go to a parametric cell design, and then we go to a complete battery pack. Here we then understand how the pack is going to behave for different loading scenarios. It can be a structural load, or it can be a thermal load, or some sort of other abusive loads which are coming onto the battery modules or battery packs. Once you have the cells, then you can quickly create a concept of the pack, or a series of concepts, and study uh, the the configuration, different configurations of pack for different loads here. Here you can see it is how easy it is to create a pack, and some quick modifications in the parameters, which then propagated to upstream analysis. And it can be further studies can be done on this packs. Another important aspect is the thermal management. So to understand or to achieve lower temperatures, or even temperature distribution within the module or the pack itself, with the different airflow condition, what could be the airflow condition which suits for your modules and packs can be studied. It can be a passive or active conditions, or different initial velocities, different flow temperatures, inlet and outlet at different locations, and what could be the cell layout. Here I have an example of a design of a module with different cell configurations, the how they are configured, and the analysis simulation results for the CFD analysis. Here I have created a parametric design. What we do here is we don't really create another design as such, but we only change the parameters of the which is the distance between the cells in this case, and the new design will then be generated. So once we have the designs, we can study the the layout, what could be the right layout for my thermal conditions, for my airflow condition, that can be studied, and accordingly I can choose my simulations. Of course, I can also study different variations for my module or pack configurations. So for a given module configuration, what is temperature propagation or internal flow simulations can be carried, and also understand the behavior of the temperatures for the at the pack level within the same platform, and without actually creating multiple files or multiple designs. All I have to do is change the parameters, because my simulation is anyway linked to the to the design. So all I have to do is change the parameters, and accordingly my design will be changed, and it will then propagate to my simulation as well. Then you may want to optimize your modules or packs for different abusive conditions, like maybe a stone impact analysis or a penetration analysis. Accordingly, you may have to optimize the structure to stiffen the structure, through maybe a shape change using by incorporating certain beads. Here in this case, a desired stiffness is achieved by incorporating beads on the pack, on the surface of the pack, to increase the stiffness of the enclosure, and without compromising or without actually changing the dimensions of the pack here. Then one more aspect is the sealing performance, because moisture can be a culprit, can play a culprit role when it gets into the cells or into the pack. That can create a lot of trouble. So optimizing the adhesive seal is also important. Here we have we have a kind of parametric optimized design of a battery pack for different uh, seal or the nuts layout. Here you can see we have we started with 200 mm. I think the distance between the hole diameters is 200. Then we changed it to a different value, and it automatically updates the design, and it's ready for a simulation. So there's a you can also compare the results within the same platform, and uh, optimize the structure accordingly, which helps improve your design. Now, apart from this, you can also look at different abusive studies for safety. It can be a crushing analysis or a penetration of the module, which is one of the regulations, I believe, in certain geos. Different locations, it can be a penetration from the top, or it can be a penetration from the side, or it can be a drop analysis, how the cells inside are going to displace when there is a drop scenario, when the module has been dropped, during the manufacturing process, or during the service conditions, etc. All this can be studied with our solutions. This is one example of side pull impact. Of course, you can also study the thermal runaway predictions at a module or a pack level. So you can accordingly strategize, how to isolate or how to reduce such conditions to inside a pack or inside a module to get away from such surprises during the working conditions. So in a nutshell, Dassault Systems has an extensive solution suite for battery industry, starting from the molecular level, which is from our BioVia sister brand BioVia, then to systems engineering and at a 3D level until the system integration. It gives a complete coverage of solutions for your battery cell, as well as manufacturing of battery cell, or for making of modules, as well as packs for your uh, vehicles, or even any other commercial purposes. So that's all I have to present.
So I would like to thank the audience also for joining us in this session. So at the end, I would like to thank once again Siddharth, Prakash, and Shikumar for joining us in this webinar. Thank you.